Hi everyone. Today we're going to be learning about logistic regression. We're going to be doing this by implementing it from scratch using just NumPy. Now, the goal of this lesson is to basically understand how logistic regression works at a core level and code it up. We're not focused on the more advanced aspects of it, such as regularization, and we're not even going to be using a learning rate as such because our focus is just on the bare bones implementation of logistic regression. The thing about this algorithm is if you already know linear regression, this algorithm is the first place where we are introduced to non-linearities. And because of this, it forms the basics, the what you're going to understand in this notebook will help you understand neural networks. So let's generate some data. We'll have 5 training examples, having 3 features each. So the way I've done it is I've stacked all the training example as column vectors and stacked them up in an array as such. Sometimes you might find people having the, the separate rows be different training examples, and sometimes it's vice versa. But anyway, no matter what the notation is, you have to just make sure the calculations work out, and that's the important part. We have a data point 1, 2, and 5. 5 being labeled as 0 and the 3 and 4 as 1. To make any kind of predictions, we basically need to multiply and add the features of the training set. And for that reason, we'll have weights and biases. Now our weights are they're gonna be three weights corresponding to the 3 features, and there's going to be one bias element. And this is how um the matrix looks for a weight. Now the core of the logistic regression algorithm is the sigmoid function, which is as such. What the sigmoid function basically does is, given any input, it squashes it down between 0 and 1. And those that can be used for making predictions or probabilities. Now let me just real quick implement that in code. And let's visualize the sigmoid function. This is how it looks. So basically, we can classify, we can use it for binary classifications more easily. But so what? We have the sigmoid function, which means that we can make predictions. Let's call it predictions A, and then actually let's define a function pred that just makes the predictions. Sigmoid. Okay, we need to multiply the weights with the features, corresponding features, and add them up. Now, as a good thought experiment and as a good mental exercise, it's always good to, especially in Jupyter notebooks, it's good to see how the multiplication um, needs to be worked out. Like, in what way do we need to do the multiplication? That's the good thing about Jupyter notebooks. We can, in the other cells, we can just test them out. So we want each of these weights to be multiplied with each of the features training example, and then add mm, so, so as you know how matrix multiplication work is the rows of the first matrix with the columns of the second matrix. So this thing should work out. It and gave us, don't forget the bias, and it gave us five predictions as such. So for the predicts function, we can just send that through the sigmoid and then return. Now let's see what our initial predictions are. Of course, this is not best practice because I'm not even sending any parameters inside the pred function, but this is just for informative purposes. Okay, cool. We have predictions from our untuned weights and bias, but so what? We need to quantify how bad a prediction is compared to the output label. So let's define a loss function. The loss function takes in predictions and the truth value and provides us with a number. Now, the reason we have this loss function rather than just taking the differences of the prediction and the actual ground truth is because if you remember, we use the sigmoid function, and because we use the sigmoid function, a normal sum of squares residuals is not going to work because that's going to give us a non-convex loss function. Using this formula, we ensure that our loss function is convex, and that means it has just one global minima, no local minimas. So let's implement this in our function called loss y star. And look at the loss. So these are all our training losses. Now if you look, our prediction for the first one is 0.92, which is way off from our truth value. That's why the loss is significantly larger as compared to, let's say, the um training example where we are only off by around 0.2, 0.19. So that's basically a little of the intuition behind the loss function. But we don't really want each individual loss. We want to see overall how bad a model does in all the examples. So we take the average of that and we get a number for our cost function. Now, basically the gist of machine learning, any machine learning model is we want to reduce the cost. So let's get to working, get to learning. But before that, let's just look at unoptimized weights and biases once again. Basically, we want to have such weights and bias such that our cost is very less. And if the cost is very less, that means we have better predictions. So we're going to do this by gradient descent. Hopefully, you already know how gradient descent works, but a little bit of the intuition is that we have a cost function, which is basically just the average of the loss over all training examples. And using this form of the loss function, using binary cross entropy, we ensure that the function is convex. It has only one global minima, no local minima. That means if we just move in the opposite direction of the gradient, we're bound to reach the global minima theoretically. And we have three weights and one biases, so we can find the gradients with respect to all these parameters and move accordingly. So we're gonna just do this algorithm a number of times, probably 25 times. First, we make the initial predictions, then we find the gradients with respect to our weights. Now, we basically want to find the derivative of this, not exactly this, well, the derivative of the cost function with respect to the weight. And the formula for that is A minus Y, and multiply that with the weights. Now, this formula you can either calculate yourself, you can find it online, but you don't really have to memorize it because all the libraries they already have that. But one thing to as a mental exercise right now, I want you to think about what the output of this will look like. Now again, this is the basically what you want to know. Like this gives the gradient of the weights across all the training examples. So have a think, and what do you think the output will look like? This, because there are three weights and there are five training examples. Now we wanna kind of sum up the weight. Like the first column is telling us how to optimize the weights in order to reduce the prediction the cost of the first example. And basically the first column is telling us that we want to reduce the weights. However, the third one is saying that we want to increase the weight. And all of these are by different magnitudes. So we can just sum them up. We can sum them up to get a like general sense of overall what our model is telling us to do. The axis is important because we want at the end we want three weights. And the sum function doesn't keep the dimensions. So let's keep let's set keep dims to 2 so we can actually um subtract this from our weights matrix. What was it? And we're gonna do the same thing for bias. The derivative is just a minus y for the bias. And I believe we can just sum this up. We don't have to keep dims because at the end of the day, the bias is just one single number. So we have the gradients of all our training examples. Now let's update the gradients. And then we're going to print out the cost so we can see after each iteration how good our model is doing. So let's run this algorithm 25 times. And now you see the cost is going down quite rapidly, I would say. And then it kind of slows down, but and then 0.03. From 1.6, we came to 0.03. How much is that? 1.6, we came down to 0.03. Damn, that's a lot. It's like 53 times. We could reduce the cost by 53 times. Okay, cool. That's just a number, right? If you want to visualize the cost over the epochs is just the how many times is the lingo using neural network is how many times we're performing gradient descent. But you can see the cost rapidly goes down. It kind of tapers off. So I'd say 25 was actually a good number. But anyway, this is just a number. Now let's see the moment of truth. How good is our function able to predict with the optimized weights and biases? How about we look at the weights and biases before that? The bias increased a little bit, the weights, yeah, they have increased a lot. Anyway, let's see predictions. They're pretty close, very close actually. But at the end of the day, remember, we want labels. We don't want numbers. These numbers are basically, you could say, these are probabilities of our testing data being one. So let's use a simple algorithm like anything that's less than 0.5. I think that's prediction less than 0.5. We will say it as 0 and anything else is 1. A less than 0.5, we make it 0, otherwise we make it 1. And then let's see, 0, 0. Yep. Using that, if we look at the accuracy, we got all 100 correct on our 5 training examples. But don't let that get you down. There's a lot of advanced concepts and fine-tuning that can be done in logistic regression if you do happen to have more complex data, which you probably will. But the goal of this lesson was to deeply understand how the algorithm works. You understood about the sigmoid function, about the loss function, and why the loss is different for logistic regression compared to linear regression. You understood gradient descent, updation of parameters, hopefully how matrix multiplication works and all that. So thank you for looking at this tutorial and all the best. By the way, guys, you can find the link to the notebook, the GitHub repo at the comment section below. And that notebook actually goes through, that notebook has some markdown which would kind of reinforce and help you learn about logistic regression better. So guys, please do take a look at it. And if you found this video helpful, hit the like. It'd be awesome if you could subscribe and leave a star in my GitHub repo. Thank you. Have a nice day.